Alrighty, howdy folks. Let's look at the section 2.5 today, chapter 2, section 5. Okay, and this should be somewhat of a short video because the content is not really all that intellectually complicated. Okay, so let's try to run through with it somewhat quickly. Yikes. Ignore that. Continuity. So let me give a definition of continuity. A function f is continuous at x equals a if limit of f of x as x approaches a equals f of a. Okay. A function f is continuous at x equals a if limit of f of x as x approaches a equals f of a. Like I said many times throughout the course, you got to kind of memorize the definitions. If you do, then you can argue with any mathematician. Like you think, oh, I'm the professor, right? So you think, I cannot talk to him, man. He knows so much. No. If you use a definition or a theorem to show and apply it properly, you can show that I am wrong. I have to eat crow. That's the beauty of mathematics and this way of learning. All right. So here, a function f is continuous. Okay. What does this mean? So now let me illustrate that with an example. Looking at this, would you say limit of f of x as x approaches a equals L in this one? Yeah. So my question is this function continuous at the graph I have given you? Is this function continuous at x equal to a? I'm asking. How do you proceed? Recall the definition. Okay, he's asking me, is this function continuous at a? What is the definition of a function being continuous at a point? Oh, the definition is a function f is continuous at x equals a if limit of f of x as x approaches a equals f of a. Cool. So let's see. What do we need to find? We need to find limit of f of x as x approaches a. Do you know what limit of f of x as x approaches a is in this case? Clear. L. Yep. Do you know what f of a is? L. Yep. Done. Limit of f of x as x approaches a is L, and f of a is L. And so, according to the definition, this function must be continuous at a. As simple as that. Piece of cake, right? Yep, it is. Since limit of f of x as x approaches a equals f of a, by the definition, f is continuous at x equals a. Cool. So I'll show you a few. This is a theoretical understanding of all of this, folks, this concept. So what's wrong with me, man? I should set that thing. So please bear with me, I apologize. So is f continuous at x equals a in this scenario? Again, let's ask. If the question is f continuous, let's ask what is limit of f of x as x approaches a is. Would you agree that's equal to L? Yeah. Okay, what is f of a? F of a is undefined. So is the function continuous at x equals a? Is the limit equal to the function's value? Nope, it's not. The limit itself is L, but f of a is undefined. So you have to say the function is discontinuous at x equals a, not continuous or discontinuous at x equals a. As simple as that, right? So when there is a hole in the graph, you have to say the function is discontinuous at the place where there is a hole, at the x value where there is a hole. Okay. Well, there are names to these kinds of, there are other kinds of discontinuities, and there are names to these discontinuities. Okay, what are the names? Here, could I do this? Note that we could remove the discontinuity by simply redefining the function at just x equals a. You can say, hey, you know what? Just take this function, man. But at a, this is undefined. Let's say I go ahead and redefine so that at a, this has the same value as what the limit is. The limit is L. So let's say f of a is also equal to L. I define it that way, redefine it that way. Well, if you did that, then the discontinuity is gone, right? And because you can so easily remove this kind of a discontinuity by redefining, we call this as a removable discontinuity. Cool? So removable discontinuity is one kind of a discontinuity. What else do we have? Oh lordy. Is f continuous at x equal to 0 in this scenario? Is f continuous at x equal to 0? Again, let's figure out what limit of f of x as x approaches 0 is. What do you say limit of f of x as x approaches 0 is, folks? Both the left-hand limit and the right-hand limit are going to infinity as we let x approach 0. So the limit itself must be infinity. And what is f of 0? F of 0 is 0 because, as you can see, I put a dot there, solid dot. So that means the function does have a value of 0 there. And limit of f of x is clearly not equal to f of 0. Limit of, let me be more precise, limit of f of x as x approaches 0 is not equal to f of 0. So our conclusion must be this function is discontinuous at x equal to 0. Cool? Let me point something out here. What if I hadn't put this dot, solid dot here? Then what would you say f of 0 is? You'll say f of 0 is undefined, right? Because you cannot say f of 0 is infinity. F of 0 is clearly undefined. And let me tell you something. Some people actually say, hey, what is limit of f of x as x approaches 0? They say it does not exist by virtue of being equal to infinity. Do you see how that is phrased? Limit of f of x as x approaches 0 does not exist, they would say. What do you mean? It exists, man. It's equal to infinity. Oh, well, when the limit is infinity, it is pretty much doesn't exist. Right? Some people argue like that. But we know there's nothing wrong with that kind of an argument. But let us try to distinguish, unless we say otherwise, that when we have limit of x to be infinity, we will say infinity. The reason I brought that out is, if we go by does not exist and the function is undefined, hey, does not exist, undefined, they are more or less the same, man. So they are equal, so the function is continuous. Don't do that. Don't make the argument that does not exist is the same as undefined, and therefore the limit and the function's value are the same and therefore continuous. Do not make that argument. Okay, cool. Moving along. By the way, what do you call a discontinuity of this kind? Because the limit happens to be infinity, we call it infinite discontinuity. Cool? All right. Let's look at this scenario. Is f continuous at x equal to 0? Is f continuous at x equal to 0? As usual, let's figure out both limit of f of x as x approaches 0 and the function's value. What is limit of f of x as x approaches 0 here? I seem to claim that this is the limit does not exist. What? On what grounds? Yeah, on the grounds that the right hand limit, tell me this, what is the right hand limit? Does that exist? What is limit of f of x as x approaches 0 plus from the right? That's clearly equal to 1, right? If we let x approach 0 from the right hand side, the y values are approaching, or what, not even approaching, they're continuously staying 1, 1, 1, 1, 1, 1, and yep, so you have to say the right hand limit is 1. What is the left hand limit? So let x approach 0 from the left, and if you do, the values are -1, -1, -1, and so on. So you have to say the left hand limit is -1. Since the left hand limit and right hand limit are not equal, we have to say the limit does not exist. Right? You remember that. Cool. What is f of 0 then? F of 0, since I put a solid dot there, f of 0 is 1. Okay. Now, is limit equal to the function's value? Nope, it's not. So this is discontinuous. As simple as that. Cool. What else? What do we call a discontinuity of this kind? We call it a jump discontinuity because as we moved from left to right, the limit jumped from one value, or the function's value, the limit, the left limit to the right limit, there's a jump. So we call it a jump discontinuity. Cool? All right. Then there are other definitions. A function f is continuous from the right at x equals a if limit of f of x as x approaches a plus is equal to f of a. A function f is continuous from the right at x equals a if limit of f of x as x approaches a plus equals f of a. Good. Is our function continuous from the right at x equal to 0? What is the right hand limit? Limit of f of x as x approaches 0 plus? Definitely 1. What is f of 0? 1. So this is certainly continuous from the right at x equal to 0. This function f. Now there's a definition called definition of a function that is continuous from the left. A function f is continuous from the left at x equals a if limit of f of x as x approaches a minus equals f of a. Is this continuous from the left? Is what's limit of f of x as x approaches 0 minus? -1. What is f of a? +1. And they're not equal. So definitely not continuous from the left. Cool. Final one. Final definition, I think. A function f is continuous on an interval if it is continuous at every number in the interval. This is a very interesting concept. Notice how mathematicians tackle continuity and other kinds of things in a whole interval. Interval means a whole set of points. First, they define at a single point. They expect you to gain a thorough understanding as to what happens at a single point. And then they say, if that is, whatever it is true for every point in the interval, then you can say that condition is true for the whole interval. Here we are talking about continuity on an interval. Well, logic says that if a function is continuous at every number in the interval or every point in the interval, then the function is continuous on an interval. Okay, and if f is defined only on one side of an endpoint of the interval, we understand continuous means continuous to mean continuous from right or left. What does that mean? That simply means, let's go back to this graph and use it to illustrate what it says there. this function is defined all the way from negative infinity to positive infinity, right? In the sense, you can plug x equals any value, and at any x value, you can figure out what the function's value is. But what if this were to be defined only from 0 to infinity, right? That means this line doesn't exist, undefined for x less than 0. In that case, could we say it is continuous? Well, it is because the function is defined only from this endpoint. The left endpoint is 0 and the right endpoint, well, there is no right endpoint. So it is defined on the interval 0 to infinity. We say it is continuous from the right. This function is continuous in that case from the right is the idea. Okay. All right. So this is all theoretical these are all theoretical concepts that I wanted you to understand. And then let's move on to solving there's a few more things. I thought we were going to problems. Anyway, theorem: any polynomial is continuous everywhere. That is, it is continuous on the real number set, that is negative infinity to infinity. Any polynomial is continuous everywhere. Polynomial? Is x squared plus 2x plus 3 a polynomial? Yep. What degree polynomial is that? Second degree. Why is it a second degree polynomial? Because the highest exponent of x is x squared. So the 2 is the highest exponent. The other one is plus 2x, I said, x to the 1. So the highest power of x is 2. Therefore, x squared plus 2x plus 3 is a second degree polynomial. So polynomials are continuous everywhere. And a rational function is continuous everywhere in its domain. That is the key. What do I mean by that? Is 1 over x minus 1 1 over x minus 1? Is that a rational function? Yep, a rational function is a polynomial over polynomial. 1 is a polynomial. What? Yep, constants are 0th degree polynomials. Please understand that. Remember that. A constant is in fact a polynomial. 2 is a polynomial. What degree polynomial, man? 0th degree polynomial. Because I can think of it as, think of 2 as 2x to the 0, 2 times x to the 0. So that's a 0th degree polynomial. Usually they say constant polynomial. And you have, when I say 1 over x minus 1, you have a polynomial 1 on the top and x minus 1, a first degree polynomial in the bottom. So that is a rational function. And this one says, this theorem says, any rational function is continuous everywhere. You gotta be kidding me. At x equals 1, 1 over x minus 1 is not continuous. There is a vertical asymptote. What in the world do they mean? Notice. They say in its domain. Is x equals 1 in the domain of 1 over x minus 1? Nope. Why not? Because if you plug 1 for x, in order to evaluate what f of 1 is, you'll get 1 over 1 minus 1, which is 1 over 0. That is undefined. Right? So 1 is not in the domain of 1 over x minus 1. Now, if you exclude that point, everywhere else, this rational function is continuous. That is the key. Cool? All right. The following functions are continuous everywhere in their domain. Polynomials, we already discussed this. Rational functions, which we had the root functions, square root, cube root, all kinds of root functions. They are also continuous in their domain. trig functions. What? Is tangent x continuous at x equals pi half? Well, x equals pi half is undefined. Tangent is undefined at x equals pi half. So pi half is not in the domain of tangent. So as long as you pick only the points which are in the domain of the function, yes, at any trig function is continuous. Okay. Similarly, inverse trig functions, exponential functions, and logarithmic functions, they are all continuous everywhere in their domain. Cool? All right. Now, as promised, let's get to point. Is the function continuous at a equals 2 if the function is defined this way? The question makes sense? Can I ask that question? I'm giving you a function, and now instead of giving you a graph of a function, I'm giving you a function that is defined the way that you see on the screen. Now I'm asking, is this function continuous at a equals 2? Can you tell me what your procedure ought to be? What's the definition of a function being continuous at a point? Oh, a function f is continuous at a point x equals a if limit of f of x as x approaches a equals f of a. Ah, cool. So, can you figure out what limit of f of x as x approaches 2 is in this case? Can you figure out what f of 2 is? The f of 2 must be easy one. So let's go ahead and answer that for me. What is f of 2 in this case? Clearly, the piecewise thing says f of x is equal to 1 when x equals 2. So clearly, f of 2 is 1. Right? What is limit of f of x as x approaches 2? Do not say 1 because it doesn't have to be 1. It may be, but it doesn't have to be. So, recall that to establish continuity, we need to verify the limit equals the function's value. So, limit of f of x as x approaches 2, let's figure that out. And so that means when x is merely approaching 2 and not equal to 2, the function is governed by that expression. Please pay attention to that. Can I say this? Limit of f of x as x approaches 2 means limit of this quantity as x approaches 2. Why not limit of 1 as x approaches 2? That is because when we say as x approaches 2, we are not talking about x being equal to 2. So this bottom part doesn't apply so far as limit of f of x as x approaches 2 is concerned. And that's why we say limit of this quantity. Okay, how do we evaluate that? As a first go, let's plug x equals 2. We get 4 minus 2 is 2, 2 minus 2 is 0. Oop, top is 0. Bottom is 4 plus 2 is 6. 6 minus 6 is 0. Oops, we get 0 over 0. That's undefined, man. Yeah, but what did I say that you need to do when you see 0 over 0 form? You need to try to simplify the expression some way. You got to do some kind of a manipulation to figure out the limit. Let's see, what manipulation do we do? Let's try to factor things out and simplify. I can write the top as x minus 2 times x plus 1 and the bottom as x minus 2 times x plus 3. And cancel the x minus 2's, and so we get limit of x plus 1 over x plus 3. Now let's plug x equals 2. 2 plus 1 is 3 over 2 plus 3 is 5, so 3 over 5. So clearly limit of f of x as x approaches 2 is 3/5. And what is f of 2? F of 2 is 1. So, is the limit equal to the function's value? Nope. Limit of f of x is not equal to f of 2. We conclude that f is discontinuous at a equals 2. Okay, there are a few problems in the book based on this concept. If you understand theoretically what all I said, and you can work problems of this kind, I'm a happy man. All right, folks, that's it. We're done with this section.